Hey, what's up, YouTube? We should be live, and I'm also going to go live on Twitch as well if I can find the link. Okay, right, it's right there. How's it going? Today is June 26th, 2026, and we will be working on coordinatization and change of basis today. In general, change of basis chapter 7, and we're going to begin with this problem. Find the change of coordinates matrix from B to B prime and then from B prime to B. Verify that they are inverses of each other for problem 12. So our basis is the set or the ordered sequence 101, 110. I prefer to write them as column vectors. I think that this is easier to read right now. 0, 1, 1. Even though the other one is easier to type in a single line exercise. So it makes sense to me why they wrote it the way that they did, but this is going to be easier to work on a blackboard, right? Okay, so if this is our original basis and then we want to convert to this new basis, 0, 1, 1, 1, 1, 0, and 1, 0, 1. To convert from one basis to another, we find a change of coordinates matrix from B to B prime. And the way that we find this is by taking the basis matrix of the new basis, append the old, and do row reductions until we get to identity on the left and then C from old to new. A little more formally, this would be written as the basis matrix of the target basis, append the basis matrix of the source or the original basis, so here is a slightly more mathematically formal way to write this, but in my head I remember new bar old, new then old, and then row reduce to I and change I and C. So what is the basis matrix? That means writing a matrix with these vectors as column vectors. So for the original basis B, well, it looks very similar to how I wrote it. 1, 0, 1, 1, 1, 0, 0, 1, 1. And then on the right-hand side of this augmented matrix, we have B prime. 0, 1, 1, 1, 1, 0, and 1, 0, 1. And now our goal is to perform this operation or this series of steps. So we do our good old row reductions. It looks like the first and second rows are in a nice state. One, 1, 0, because we have a pivot in the first entry. Yeah, we have 1 as the first pivot and then 1 as the second pivot as well, right there. Then in the third row, we could subtract the first row. That'll zero out that entry below the first pivot. So 1 minus 1 is 0, 0 minus 1 is negative 1, and then 1 minus 0 is 1. 1 minus 0 is 1, 0 minus 1 is negative 1, and 1 minus 1 is 0. Then from here, now we can... Here, let's start from the bottom to see if we can work more in place. Hey, what's up, pumpkins? How's it going, dude? How are you, bro? Let's see. That didn't work. Why didn't that work? Bro, this is crazy to me. Why doesn't this work? Dang it. Dude, this is so confusing to me. Why is this not working? Oh, well, whatever. Let me close that. How's it going, dude? Oh, and now Twitch chat, this is behind. Yeah, this isn't reading the newest. Oh, that's confusing. Also practicing presentation and teaching, and it's I don't know, I just think linear algebra is kind of the most important math nowadays. It gives people an opportunity to jump in. I'm doing good. Thanks for asking. Totally. I'm also adding more calculus and more representation theory as well. So what's up, Haku3107? What do you think, dude? What are your thoughts? Do you think it's too much linear algebra? What kind of math do you wish I studied instead? Okay, so now the second row added to the third is 0, 0, 2, 2, 0, 0. And now I will also divide that row by 2. Then let's subtract this row from the second row. 0, 1, 0. 1 minus 1 is 0. 1 minus 0 is 1. 0 minus 0 is 0. And then now we can subtract the new second row from the old first row. So 1 minus 0, 1 minus 1, 0 minus 0, 0 minus 0, 1 minus 1, 1 minus 0. And now this is in the form of I and our change of basis matrix C. Okay, so that was what we get if we go from MB prime to MB. So the change of coordinates matrix from the first basis to the second basis is this. Yeah, I want to work every single exercise in this book is the idea. Like, I want to solve this book. I've never solved a full book before. But I'm taking like a problem from every different section, and instead of just going and doing all the problems in a section before doing the next section and doing all the problems, I'm doing a problem from every section at a time. Yeah, I don't know. Thoughts? Any opinions there? I would appreciate feedback. Okay, then now to find C from B prime to B, we do MB append MB prime, and we row reduce to that. So let's copy this. I mean, you'll notice that we're getting more calculus and we're getting more representation theory. And I am very tempted to move on completely. But yeah, all the exercises are getting harder every time. Okay, so now Well, we could rearrange the first and third rows, or the first and second rows. Yeah, the first and second rows would be nice to interchange. 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0. Now, I'm also going to subtract old row 3 minus new row 1. Or you could think of old row 3 minus old row 2. So 1 minus 1 is 0. 0 minus 1 is negative 1. 1 minus 0 is 1. 1 minus 0, 0 minus 1, and 1 minus 1. Now, add the second row to the third. 0, 0, 2, 2, 0, 0. And again, we get this kind of nice property. Now we subtract new row 3 from row 2. 0, 1, 0. So 1 minus 1, 1 minus 0, 0 minus 0. And I think that we're getting to the same matrix that we had before. So 1 minus... So now we're doing row 1 minus row 2. 1 minus 0, 1 minus 1, 0 minus 1, 0 minus 1, 1 minus 1, 1 minus 0. And now we get the identity matrix by subtracting the third row from the first. So negative 1 minus 1. Okay, so it's not the same matrix this time. Negative 2, 0, 1, 0, 1, 0, and 1, 0, 0. So then therefore, our change of basis matrix from B prime to B is negative 2, 0, 1, 0, 1, 0, 1, 0, 0. So that's our second change of basis matrix. This was our first. And now we want to verify that C B B prime times C B prime B should be the identity matrix. So that they are inverses of one another, in other words. Something kind of feels like something might have gone wrong, but maybe not. We'll find out. Could be wrong. Okay, now from here, dot product of first row, first column, we get a 1. First row, second column is a 0. First row, third column is a 0. Second row, first column is a 0. Second row, second column is a 1. Second row, third column is a 0. Third row, first column... Yeah, something went wrong. Dang. Third row, first column, we're getting a negative 2. Third row, second column, we get a 0. Third row, third column, we get a 1. So something went wrong. I felt like, what? Negative 2 doesn't seem right. I was getting some alarm bells in my stomach when we did this one. Okay, so let's write out what our steps were, and let's see where the mistake happened. How's it going, everybody? How's it going? Dude. Pumpkins, what are you up to today, bro? Are you studying as well? I don't know how to reset. Can I manually refresh this or something? Refresh cache. There we go. Okay. All right, now we got chat on screen. Okay, so something went wrong. That -2 was troublesome. Okay, so if I... Oh, wait, yeah, what am I doing? If I add the third row to... I'm supposed to add the third row to the first. I subtracted the third row from the first. There we go, that fixes it. -1 plus 1 is 0. So that's where the error was. I think that this needs to be a 0. And now, if this is changed to a 0, now the third row first column is now correctly 0. Therefore, they are inverses of one another. All right, we did it. We frickin' did it. Is there any interesting note? Yeah, so note in this, I didn't even pause and think about it. Note that the second vector in this basis is the same, and the first and third are just swapped, right? So it's just a permutation of the same basis. It's the same basis vectors, but they're just permuted. This is a permutation matrix. And it permutes rows 1 and 3. So that's cool. Now we're done with that exercise. Y'all, feedback is a gift. It always is. So if y'all want me to stop doing linear algebra, I'm definitely all ears. We could definitely do that. 7.2, matrix representations and similarity. I'm starting to get a little tiny bit bored of linear algebra, but not really. Like, I do want to continue going. But I am starting to feel like I'm not really sweating as much as I used to about this material. So I kind of want to add in some new material. While continuing to work systematically somehow and continue making progress and actually solve the entire book. So we've got section 7.2, which is on matrix representations and similarity. Yesterday we had a regular in the chat asking about whether similarity creates some kind of isomorphism. And yeah, like similarity of matrices like we definitely get some theorems that are essentially like isomorphism theorems. We get some theorems like the fact that similar matrices have the same eigenvalues. Similarity of matrix representations. Like two similar matrices represent the same linear transformation, which is neat. What's up, Zafarb? How's it going, bro? What are your thoughts, Zafarb? For me to continue getting better at math effectively, do you think I should keep working through this book and try to solve every exercise? Or move on to another book? like more advanced linear algebra and just keep getting better at linear, or add in a new topic? Like, are you all getting sick of seeing my face studying linear algebra every day? That would be understandable. I would understand it. Find the representations RB and RB prime, and the invertible matrix C such that the way that they're writing it, such that RB prime, the new representation matrix, equals C inverse RBC. For this, so we're finding representation matrices for this linear transformation. Okay, so first we write the nice little solution thing. So RB is the representation matrix relative to the standard basis Oh, wait. So this would be TB1, TB2, TB3. And we're noting that then this is relative to the standard matrix, or the standard basis. So let's just do this one first. So T of B1, T is a reflection through this plane. How do I write a reflection across a plane? Yeah, applying it to other math makes sense. That's fair. I mean, I do think that I have a fairly good grasp of linear algebra. We're starting to apply it to representation theory is the thing. Like, I am starting to apply it, and the amount of time that until the next time that I revisit a topic is getting longer every time. I believe very much in spaced repetition, but I do wonder if we're not doing long enough spacings. Like, we could be getting longer spacings between revisiting linear algebra topics. Like, spacing right now is increasing linearly, but it should increase super linearly somehow. But then on the other hand, I think that linear algebra is a nice topic because it's relatively, for me, the optimal spacing is when I almost forgot it. I'm starting to be like, wait a minute, I have to remind myself about this. Yeah, I don't think for me I'm almost forgetting it yet, but like, I do feel that it's getting just like a little bit harder each time. Yeah, I probably should move on. I think what's going to happen is I'm going to add a totally new topic somewhat soon. I'm thinking like an intro to proofs or like some kind of proof oriented math. Something that like it might be abstract algebra or it could be basic mathematics by Lang. I'm kind of excited to try adding in Lang's basic mathematics, which is like a proof oriented high school math, which I think is cool as an idea. Like I kind of want to learn that. And there's just the fact that right now I'm still practicing teaching. It's not just purely my own understanding, but my ability to teach this material as well. I don't know. We'll see. We'll see. I'll take that feedback, and consider it. I do think I'll probably run a poll and see if people want a new book, and I think that the answer will be yes. But it could be an upgrade of linear algebra to proof-oriented linear algebra. So we could introduce in proofs through Axler, through Lang's high school book, or something like abstract algebra, I think. I don't know. I'll probably put it up as a poll and just see what people want. Okay, so then let's see. TB1 is a reflection of 1, 0, -1 through the plane x plus y plus z equals 0. How do I find this? What does that exactly mean? So the plane x plus y plus z equals 0 is a two-dimensional subspace, right? Because a plane in R3 space it's two-dimensional, yeah. And I think that this equation defines the null space of one equation and three unknowns. And this is the span of two vectors. So when y is 1 and z is 0, then x is -1. And then I like to scale that. Similarly, we have that. Then reflection of B1. What do I find? I find like the projection. We find shoot. Anyways, time to lock in. You feel like linear algebra is not interesting by itself? I love it. I love linear algebra personally. I think it's very interesting in itself. So maybe that's a part of the difference, I guess, between us. So I can find the projection to W and the orthogonal projection of W. Then the reflection of B1, I think, is defined as its projection on W minus its orthogonal component. So we find the orthogonal component, which is B1 minus B1, the projection of B1 onto W. Is this the right way to do it? Okay. Let's see. Yeah, I think that we're on the right track here. So we find B1, the projection of B1 onto W. If oh wait. Oh no. We just need to find the okay, I can cheat because I know that an orthogonal vector in R3 to two vectors is the cross product. But I feel like I should be able to do this without that fact. Let's see. If I review this section, I think that there will be an exercise similar to this one, and I can just mimic it. But I want to, for the sake of learning this material, really try to figure this out on my own, because I think that we have all the tools that we need from previous sections. In particular, yesterday I just studied orthogonality, so I feel like I should be able to reconstruct this one a little more easily, but So B1W is going to be some XYZ such that B1W. Oh, wait. We really want. Yeah. So the projection of B1 onto W. Well, we can project it to any point in the span of the plane. No, something just feels super wrong. Like I want to say that it's the sum of the projections of the two vectors, but I don't know if that's true. Let's recall. For any two vectors, the projection of V on W is V dot W divided by W dot W times W. So if we have two of them, do we just add them together? Hey, what's up, Ta? Yeah, my interview a couple days ago went pretty well. It's unfortunately not an actual job. But it's training, like a public school certification program. So it would be, so that I can get licensed to teach next year or possibly next spring, which would be great if I could, because I just feel like I'm ready to go right now for middle or high school. I could teach today. Like I don't think that I don't know. My thought is that I'll learn. Oh, disconnected, reconnection successful. I think I'm ready to go today for a private school or like with motivated students. I think I would need certification potentially to teach a public school. I don't know. I just don't know enough. I don't know enough. I don't know what I don't know. And I feel like I need more. I need some mentorship. But I think with the right mentor, I could get started this fall. No problem. I feel confident about that with under the right mentorship and like the right classroom or something. I think that this is what we want to do. I just want to convince myself of why that would be true. Because I think the thing is that we can take any scalar multiple of the first and the second, and this is still going to be a projection onto the plane, I believe. and then we find an orthogonal component. So I think that this is simplest if we project to both of them and then add. I'm kind of struggling with this one today. If your basis is in the plane is orthogonal, then you can surely project separately and then add the projections. That's what I'm thinking. Not sure if it's not, though. Connection been bad. Not sure if it's just me. It is. It's still in the span. Yeah. I mean, this is my thought, too. Like, I think any scalar multiple of the two would then be in the span. Like, I could project to any point on the plane and then construct a different orthogonal component. But then, like, why wouldn't I just project to the first? Couldn't I take 0, like K2 to be 0 in this? And then I would just be projecting to the 1, to the first basis vector. I guess, yeah, I need the... That would only give me one point, one vector, whereas I want a span of something. So I think the fact that... Okay. I think that this is where we're getting somewhere. So this is going to be the projection onto the entire plane. V dot W1 is going to be (1, 0, -1). Yeah, dot product with 1, -1, 0. V dot W2 is 2. W1 dot product with itself is 2. W2 dot product with itself is 2. And just, yeah. I think writing those, bring this down just as like a little reference. We're going to have K times V dot W1, W1 dot W1 times W1 itself, which was 1, -1, 0. 1, -1, 0. Yeah, now we're going to get, I guess, 3 equations and 2 unknowns? Yeah, 3 equations and 2 unknowns gives us a one-dimensional subspace. And now, yeah, we're going to get to our one-dimensional subspace that we're looking for. Heck yeah, okay. We're getting there. So V dot W2 is 2, W2 dot W2 is 2, W2 itself is 1, 0, -1. So if I don't freaking know, dude. Like, if we say X is in W per, or in, I think I only need... Yeah, I don't need to find the entire subspace. I only need to find one. So I think I just add the two, which I can concretely compute. Like, I think I can just take K1 to be 1 and K2 to be 0. Yeah, because the projection of a vector through a plane should just be a single vector. It shouldn't be a span. Right? No, because if I project onto that plane, there's the... Yeah, if I project onto the plane, then there's infinitely many points that it can project to. I have a hard time visualizing 3D space with this kind of stuff. But in particular, I can take a particular solution and find the orthogonal decomposition. So if I take this particular solution with K1 being 1 and K2 being 1, but then why not just make K2 0? That's where I'm... Well, I guess I need to ensure that... I don't know. I'm pretty confident that I can take this as a projection and then subtract from B1, and then that finds the orthogonal component. I really think that there's a nicer solution on this, but I just want to complete this solution, then read the section and find out how I could have done it better, I think. So whatever I label this as... Oh, this is B1 onto the plane W, but this particular point in the plane, which is one part of one vector and one part of the other vector. Yeah, well, we have 1/2 plus 1, negative 1/2, and 0, minus 1. So then, therefore, because B1 is B1 W plus B1 perp, then basis vector 1, 0, negative 1. Well, let's write this a little nicer. Then B1 perp, which is what I'm really trying to get at, is B1 minus B1W. B1, again, was 1, 0, negative 1. 1, 0, negative 1 minus our orthogonal projection, 3/2, negative 1/2, and negative 1. And now this is 1 minus 3/2, 0 plus 1/2, and negative 1 plus 1. Okay. So now I have the orthogonal component, so the reflection is going to be the projection minus the orthogonal component. And the projection we found is 3/2, -1/2, -1. 3/2, -1/2, -1, minus -1/2, 1/2, 0, which is now 3/2 minus -1/2 is 2. -1/2 minus 1/2 is 0, and then -1 minus 0 is -1. Okay, and then I think we go through the same process for TB2, which is kind of crazy. TB2 is going to be the projection onto W minus the projection onto the orthogonal component. The projection of B2 onto W, I'm saying that it is B2 dot the first basis vector, the projection onto the first basis vector plus, and this is the part where I'm just super uneasy, like that I'm choosing this particular point. Like, why not just choose... Well, yeah, I guess this guarantees that the point is on the plane, whereas if I only project across the point spanned by the first component or the first basis vector, then yeah, I think I see it. It doesn't guarantee that that point is on the plane. Well, So people are asking, like, if I have a good enough... Hey, what's up? How's it going? Somebody saw me a few days ago on YouTube. Yeah, I'm here almost every day, dude. -1 for the middle component of TB1. Oops. Oh, thank you. Thank you, dude. That would have been an annoying ass error. I appreciate that. Oh, okay. Stupid little error there. Like, yeah, I want to understand why a little bit better, why I think that I should arbitrarily add one part of the first and one part of the second. I need to revisit a little bit better. But, well, B to perp, I found this earlier via B2 minus B2W, but I just said that B2W is this first part, so I can double this entire first part, right? B2 dot W1, let's write out our facts based on the fact that I found W1 and W2 here, then B2 dot W1 1, -1. Let's just write this here. B2 is 1, -1, 0. 1, -1, 0. B2 dot W1 would be 2. W1 dot W1 is 2. B2 dot W2 is 1. W2 dot W2 is 2. So then B2, yeah, the projection onto W1 then is 1, -1, 0. It was 1 times that. And that this 1/2, this is the coefficient of the projection onto W2. 1, 0, -1. And this is a projection onto the sum of those two vectors, which is certainly on the plane spanned by them. Oh, and here, I think I want to just copy this over. So here I found this, and then the second basis vector B2 once more was 1, -1, 0. 1, -1, 0. Did I get this? Wait. A vector is... projection of a vector onto a space is this. So then... yeah, B2 perp is B2 minus B2W. Okay, that is correct. Let me just clean this up a bit. Okay, now we have 2 plus 1, -2 plus 0, and 0 plus -1. here was a reflection of the first basis vector. And now we do the same thing again, finally, for TB3, which is going to be B3 Coming back to my previous work, we want to compute this. Did I cut or... No, I correctly copied that. Yeah, I copied. So now we're working with B3 being 1, 1, 1. So then this projection, I think, is one, I'm looking near the bottom of the screen, that green W1, and B3, dot product of those two is 1 minus 1, so that's 0. Oh, and all of this is multiplied by W1 and W2. Oops. So the first part is 0, and then the second part is 1. Yeah, the second part is also 0. Interesting. Okay. Yeah, because this point lies on the plane. Okay. So this is 2 times 0 minus B3. Something feels so wrong then. If the reflection of a point which lies on the plane is the negative, something feels broken. Now I feel like something is broken. Now I feel confident about it. Because 1, 1, 1 is in W, so T of B3 should equal itself. So the projection of B3 onto W should be itself. So I think that then this claim that this is the projection of the vector onto the plane, this seems to be broken, which is where I felt like I was fairly uneasy. I was like, something doesn't feel completely right about this one. I think that projection, yeah, okay, cool, works only when W1 and W2 are orthogonal. Try to draw W1 being very close to W2 and project some vector onto that. Oops. Okay, there we go. That works when B3 already lies on the plane. Not sure what that comment was. But yeah, okay, so I was assuming that we had an orthonormal basis for, I believe, for W. Yeah. All right. So I gotta pee real quick. I'm gonna be right back. We messed up on an exercise. Let's go. That's a good thing, y'all. That's a good thing. That shows that that I am human. I am not an AI chatbot. I'm telling you, I'm not I'm not ChatGPT. I make mistakes. Everybody makes mistakes in math. So we're going to do a little bit of review of orthogonality properties, and so that we can get the beginning of this of this exercise. Yeah, last night I did not study orthogonality well enough, actually. So I do feel like something was wrong. One thing is, if we had gotten to the last section of the previous chapter, the projection matrix, which I didn't review, I think that I can write down the projection matrix and then we can compute the projection much more easily. Yeah, I think using the projection matrix might help here. Okay, be right back. I gotta pee. So what I was doing, what's up, Samya? How's it going? Good to see you. I have an important meeting in an hour. So one issue that I had was that I was assuming an orthonormal basis set of solutions to this equation. Oh, music is loud. Oh, my bad, my bad. Okay, now it should be fixed. Yeah, it's kind of complicated to describe it, but it's that kind of technical error comes up for me because I stream vertically for guitar and horizontally for math, and I updated my scenes in a way that like updated one but not the other. So the vertical stream was still playing music from the Be Right Back, and then the horizontal scene was back. So now it should be fixed, right? So that is, here we have this theorem 6.3 that says projection using an orthonormal basis. Let V1 through Vk be an orthonormal basis for a subspace I suppose Steinberg uses subspace this way. Yeah, let me know. I think that the audio should be fixed now. And let B be any vector in Rn. The projection of B on W is BW equal to the projection onto the first basis vector, yeah, plus all the other projections onto all of the other basis vectors. Therefore, we can recover our previous solution by finding first an orthonormal basis for W being the solutions to that equation. So we found that W is the span of two vectors So we apply the Gram-Schmidt process to find a orthonormal basis for W. Don't forget to normalize this. So we need to normalize the second basis factor minus its projection onto the previous subspaces. So minus 1, 0, 1 dot product with W1 prime divided by W1 prime dot W1 prime times W1 prime. So W1 prime dot product with itself equals 1. And then dot product with 1, 0, 1, 1, 0, negative 1. My bad. Almost made an oopsie right there. 1, 0, negative 1. Yeah, 1, 0, negative 1 dot product with that is 1 over root 2. W1 prime. One minus 1/2, 0 plus 1/2, negative 1 minus 0. Something feels just ever so slightly gross about this, but this thing dot product with itself would be 2/3 times 1/4 plus 1/4 plus 1. Why does something feel off? 2/3 times Okay, 1/4 plus 1/4 is 1/2. 1/2 plus 1 is 3/2. Okay, so I do think that this vector is normalized. Okay. Square root of 2 over 3. Will you change my basis? What's up, Locke? How's it going? I have no idea what that is supposed to imply. Changing somebody else's basis. Okay, so now we have... So, now we have a orthonormal basis. 1 over root 2 times 1, negative 1, 0, and root 2 over root 3 times 1/2, 1/2, negative 1 is an orthonormal basis for the plane of solutions to this equation. Then T being defined as a reflection across this. First, let's compute these simpler ones. T of E1, which we will need soon anyways. T of E1 this is going to be the projection onto the plane minus the orthogonal component. And the orthogonal component is E1 minus the projection. So this would be 2E1W minus E1. And now I can find the projection of E1 onto W being the projection of E1 onto W1 star and W2 star or something, where this is a new transformed orthonormal basis for W. So I'm just going to write that the projection of E1 onto W is the projection of E1 onto W1 star plus the projection of E1 onto W2 star minus E1. This is E1 dot W1 star divided by, and note that because the basis is orthonormal, then the magnitude of each vector is 1, so the dot product of each vector with itself is 1. So this is that times W1 star plus E2 dot product W2 star times W2 star minus E1. And now these are relatively easy to compute. E1 dot W1 star is the first component of W1 star, which is 1 over root 2. And then W star itself is 1 over root 2 times the vector 1, 0, negative, nope, 1, negative 1, 0. 1, negative 1, 0. The second, this is E1 dot W2 star. W2 star, the first, let's just write out all of W2 star first. Copy. So W2 star is this, and then the first component of this would be 1 over root 6. You can see that as square root of 2 divided by 2 is 1 over square root of 2, and then divided by square root of 3, that's 1 over root 6. E1, of course, is 1, 0, 0. Now, we can clean up things a bit. 1 over root 2 times itself is 2, and then 1 half times 2 is 1. So we have 1, negative 1, 0. And then we have here, if I multiply 2 times the vector, that makes our lives easier. Okay, here, square root of 6 is square root of 2 times square root of 3. So I see that this simplifies as 1/3. And then 2 times the vector is 1, 1, negative 2. Then we subtract 1, 0, 0. Now we have 1 plus 1/3 minus 1 is 1/3. Negative 1 plus 1/3 is negative 2/3. 0, so this last component is minus 6. So supposedly, this should be the reflection of E1 across the plane. Every rotation and translation can be decomposed into composition of reflections. I think I've seen that, yeah. This is kind of used as a defining property of projective geometric algebra. Interesting. Negative 2/3 is the last... Dang it! Vlada keeps catching me on this. Oh, yeah, damn it. Yeah, you're right, you're right. Oh, no. Thank you, dude. No, thank you. Bro, what would I do without you? Negative 2/3. Yeah, 2 times 1/3. Ugh, yeah. I wonder if there's a nicer solution, but I think that this approach is now working. So if I refactor my solution, everything applies up to here. As long as I change E1 to E2 everywhere. So reminding ourselves that W1 star, W2 star are, let's just copy them. Let's not. I remember 1 over root 2. Here it is. Let's shrink this down a little bit. So there's W1, W2. Just as a reminder. So the second component of W1 star is negative 1 over root 2. And then W1 star itself is 1 over root 2 times 1, negative 1, 0. E2 dot W2 star would be 1 over root 6. And W2 star is root 2 over root 3 times, 1 half, 1 half, negative 1. E2 is 0, 1, 0. Again, all of this simplifies as 1/3 times that vector. And so if I double the vector, I get 1, 1, negative 2. Zero, 1, 0. And now, negative 1 plus 1/3 is negative 2/3. 1 plus 1/3 minus 1 is 1/3. And then 0, negative 2/3, 0. So now this is TE2. I really wonder if there's like a nicer solution for this. So this is fairly similar, but not exactly the same. TE3 is the same process. How much is different? I'm just gonna do it again. E3 dot W1 star is 0. And E3 dot W2 star is negative root 2 over root 3. which is then negative 2/3 times 1, 1, negative 2 minus 0, 0, 1, which is then negative 2/3 minus 0, negative 2/3 minus 0, and positive 4/3 minus 1, which is 1/3. Let's see. See, this is why I hate numbers. Yeah, me too. It's so easy to make mistakes with numbers. Everything could go right and the numbers could go wrong and then everything goes wrong. Yeah, I'm glad that I had help in the chat catch me on that one. There is always some super elegant way to do it, but you found a logical way to do it yourself, and it works. Okay, let's go. Yeah. I was thinking, speaking of elegant solutions and stuff, I was thinking at one point that W is the span of these two vectors in R3, right? So then I can find an orthogonal third vector using the cross product. I probably should be doing that, I think. I bet that there's a solution just using the cross product to find W perp. But, alas. If I have W, can I immediately find W perp? Not as a cross product, but knowing that R3 decomposes as a direct sum, I bet that I could have found the basis vector for W perp and then project, I guess I would project each of the basis vectors onto W perp. Oh, dude, this would have been so much simpler, right? Yeah, if you use a cross product, then you get one angry viewer in the chat. That's exactly why I didn't do it. It crossed my mind. And I was like, I bet Locke is going to tune in, and then he's going to get angry at me. Bro, I think that this would have been way simpler. I guess I would have needed to find I think that there's a different Yeah, I think that that would have been so much nicer. I could have more easily found somehow, and I'm thinking about how do I find the basis for W perp more quickly? If I know that these two span W, how do I find the third basis vector? Um, and then, yeah, then I could have found the projection of each of these vectors onto W perp, and then say that the reflection is the like the rest would have been much easier, I think. Yeah. I mean, I still would have been using a lot of the same properties, that the reflection is the projection minus the orthogonal component. It's just that I'm doing a crazy long way around to find the projection. Also, now that I do have an orthogonal basis, I think I can find the projection using because we have an orthogonal basis, I think that we can use the projection matrix, which is something like this, or A transpose A inverse A. I think it's the second one, actually. Because I did the hard work of finding the orthogonal basis using... Yeah, it's the second one. It's the second one. But I found a solution that was a little gnarly, and I could continue this process in order to do it again and again for our other basis. But I think that there are these two other alternatives that I want to try to figure out. Find a basis vector for W perp. This is one alternative. Alternative 2 is find the projection matrix using... because the projection matrix requires your matrix A to be orthogonal, right? No, that's not even true. Dang it, okay. Oh, okay. Using P equals A. Okay, here we go. A transpose A inverse times A transpose. I could have done this from the very beginning using the original vectors. But then the fact that we converted our basis to an orthonormal basis, then the projection matrix satisfies some nice properties, because this would be A inverse, A transpose inverse, A transpose. And A inverse is equal to A transpose for an orthonormal, or for an orthogonal matrix. Is this? Yeah. The projection matrix is AA transpose when our basis is an orthonormal basis. I use that property right there, that A inverse equals A transpose. So this is kind of like alternative 2 and then alternative 2 prime, I think, uses the fact like that we have a simpler computation of P. So let's see if this works out in the first place. P equal AA transpose, where our orthonormal basis was this. So (1 over root 2, negative 1 over root 2, 0. 1 over root 2, 1 over root 6, negative root 2 over root 3. I want to factor out some square root of 2's to make my life easier. So if I factor 1 out of the first and 1 out of the second, this is a little ballsy, I feel. So in that last entry, if I factor out 1 over root 2, we need to multiply the numerator by square root of 2. Yeah. And we do the same thing here. 1, 1, negative 1, 1 over root 3, 0, and negative 2 over root 3. We could factor out a 1 over root 3 if that makes our life life's even simpler. And we would factor one out of both of them. So then we'd be factoring out 1/3. I don't know if this makes our lives any simpler, really. Now we have... Yeah, probably that one wasn't necessary, I feel. But in any case, now we have 3 plus 3. -3 plus... Wait, shit, really? -3 plus √3. Um... 0 minus 2√3. -3 plus √3. 3 plus 1. 0 minus 2, 0, -2√3. Yeah, this should be a symmetric matrix. So I expect this next one is going to be -2, yeah, and then +4. So... Bro, I'm going to leave that as it is. Yeah, Vlada. Yeah, the point for me right now is to play with the solution and like really try to work through this exercise really fully and like work it multiple ways and like see and really try to internalize the different approaches and different solutions. Because the point is not to find the answer, but to find the different problem-solving strategies of how to solve a problem like this. Or really any kind of problem. Like, try to get some basic kind of assembly language, direct approach, which involve projections and converting using Gram-Schmidt process. Then see, like, oh, was there a nicer solution for this? May I recommend the GA approach? I don't know that. I don't have a book on GA. Someday, maybe, but not right now. Not today. Yeah. And yeah, in the end, really, like, approach 0, which was my first consideration, if I just cared about the solution, this one would have been the easiest. I mean, I could find W_perp as a span of something where I know that it's an orthogonal vector to W1 and W2 is the cross product. Like, because we're in 3 dimensions, this would have been the simplest solution, I think. Like, it's not a mystery on, like, how to find that orthogonal vector. Then we could have done the decomposition. Yeah, man. And, like, right now I'm noticing this alternative, and I wanted to see So here is the projection matrix to connect back to something I didn't get to yesterday, actually. What happens if I do the projection matrix with vector E1? I want to see if I got the right solution earlier. Like, do these two match? I hope so. Let's see what happens. Well, yeah, this is going to be... God, -3 plus root 3? Really? -2 root 3. I do not think that this is what I got earlier. Unless I'm just not seeing why these are equivalent. Okay, so the first component is 1. The last component is square root of 3 over 3. Negative root 3 over 3, which is -1 over root 3. And then I'm going to think about that second component, but let's see, did we get TE1? Oh, wait, but this is the projection. So then TE1 should be the projection of E1 onto the subspace minus the projection onto the orthogonal component. And I found earlier that that should be the projection VW perp. I gotta go in 15 minutes. The orthogonal projection, the orthogonal component is, the vector minus the projection. I mean, I never thought of it this way, but this, I suppose I could factor as 2p minus I times E1 to get a little fancy. So then 2p minus I so 2 times p would be 2/6, which is now 1/3, minus I, which we can calculate in a second, times E1. 1/3 times 6 is 2. Negative, Yeah, this is negative 2 over root 3. Wait a minute. Better yet. Let's keep a third factored out. I would just do this directly, but I just want to show it, I suppose, minus. I can factor out 1/3 out of the identity matrix. So now I just subtract 3 along the diagonal. 3, 1, 1. Keep the rest. Negative 3 plus root 3. Oops. Yeah, I just don't remember that negative 1 plus 1 over root 3 in my first solution. So now I finally have a claim that this is t of E1. And is this same as the first approach? I don't think so. So I think something went wrong. I mean, if I missed a 1 over root 3 somewhere, multiplying by 1 over root 3, no. I mean, the first one looks a lot nicer, so... You already calculated PE1. Why are you doing it this way? Because we're finding TE1, not PE1. So... Oh, you're saying, yeah, I've already found PE1. Well, I almost did. I started... I felt like something may have gone wrong in that middle component, and I still do. I don't know, man. I gotta go. I feel like I practiced today, and I feel like we are getting to the section of the book, like, orthogonality is not an area of linear algebra that I feel as comfortable with. So, coming up, somebody earlier was saying, like, hey, why are you still doing so much linear algebra? It's because the second half of this book, or like the last chapters, I definitely think I'm definitely weaker on. So we may do something like take chapters 1 through 5 and upgrade those to Axler, but then keep going with Fraleigh on these last sections. That might be what we do, or I start just adding a different subjects. But there are the easier chapters of Fraleigh, and I think we should start spacing out, longer spacings till the next time that we revisit just like simple matrix calculations and stuff like that. Like, I do agree with some viewers that maybe we should be upgrading those streams. So thanks everybody for watching. I think we almost solved this problem. I think I've found some progress, some partial solution. But I think that this approach works. I suppose I can check also with the cross product approach, because I can find the cross product fairly simply. Yeah, thanks for watching. I gotta go. Bye, chat.